Okay. Huh? No, this is picking up. So we can proceed like we did yesterday, although now we have only 1 hour instead of, and then Guillermo will start with the second. So but they should be shorter things. I would actually say that look at the 2 exercises and pick which one you want and start with. I don't think. Well, no. Let me take that. Let me take that back. Let's start with one. So think about it for 15 minutes or something. Then we'll go through it. Then we'll go through number 2. But if you're completely stuck with number 1, first you should ask. But if you're still stuck, you can also try number 2. So kind of the first exercise, so this is directly from Kovtchikov-Levin. In some sense, this is something that if you would ask in a perturbation theory the question, okay, I have a single quark, what is the gluon field of that quark perturbative to lowest order? So you would just look at draw the diagram, you would kind of try to follow the Feynman rules. You have fermion coming in, fermion going out. You have a propagator, because kind of if you ask if you're doing a cross-section calculation, you truncate the external propagator. But if you actually want to calculate the field, the field is the source of radiation times the propagator, right? You would, like in classical electrodynamics, you would calculate the gauge field emitted by some charged particle by taking the current and then taking the propagator, right? So this is so we kind of try to follow the Feynman rules. We put a Feynman gauge propagator, a vertex, and then we put a factor that says that the outgoing particle also has to be on mass shell. And then we have to remember that we want this in the iconal limit, so p plus is much greater than k plus. So we use that everywhere you can. Okay, so I didn't remind myself of all the intermediate steps here, and but let's go through this. So, so as I said, the starting point is something that if you say that I want to do perturbation theory, I want to calculate the color field of a point charge or electric field of a point charge moving at high velocity, this is the kind of expression you might want to write down, right? So normal Feynman vertex propagator, Feynman gauge propagator, on shell condition, putting the outgoing quark on shell. Okay, so let me just start calculating this. So first, of course, you use the iconal vertex, which says that this is 2I times p mu, and the spin is conserved, so the spin of this guy is the same as the spin of this guy. Good. So p mu only has a p plus upper component. So, and this p plus you put together with this delta function that puts the guy on shell. So if I expand out the argument of the delta function, so this is p minus k squared is p minus k plus times p minus k minus the transverse components. Now my incoming p minus is 0. K plus is small, so I neglect this. So the argument of my delta function becomes this, okay? So now I want to use the delta function to fix what is k minus. Because there's a k minus, I have an integral over k minus here. So I use the delta function to get k minus. If I have this p plus, so if I have a p plus times delta function, something that is p plus, it kind of, I pull this p plus out of the delta function and it becomes a 1 over p plus, which cancels this. So this combination p plus times the delta function, I can just write as delta function that sets k minus to some value. What value? Some very small value, because p plus is large, right? So I can say that this delta function sets k minus to 0. Good. So this has two consequences. First of all, the propagator. This propagator is just the transverse momenta. Right? And this is a very typical thing in this kind of BFKL physics, high energy physics. These kind of T-channel propagators are just dominated by transverse momenta. If you somehow, again, these ladder diagrams that you have seen that Leif was drawing, typically the vertical lines, the propagators actually just have transverse momentum because of this kind of an approximation that we have a strong order in rapidity. This leads to propagators, T-channel propagators only having transverse momentum. Good. So my propagator is only transverse. So now nothing depends on k plus. I kind of completely neglected k plus because it's so small compared to p plus, which means that the integral over k plus gives me a delta function in x minus. The integral over k minus I do using the fact that this gave me a delta function. And then I have this annoying integral. So this is a two-dimensional propagator, okay? And there's many ways to do it, and I'm not sure what is the elegant way. I'm kind of a little bit waving my hands here. So somehow, for me, the point is that I know that the two-dimensional propagator in coordinate space is a log. Okay, so let me somehow try to justify that. First of all, if I calculate gradient nabla squared acting on a log, I hope if I'm doing this right in radial coordinates. So r is the absolute value of x. So I don't have an angular part. So if I just operate on a log, I see that I actually get 0, except that this intermediate steps in this thing were kind of not very well defined at r equals 0. So a two-dimensional nabla squared operating on a log is 0 except maybe at 0. So that kind of looks a little bit like a delta function. How do I see that it's a delta function? So here I'm kind of completely cheating, right? To see that this is a delta function, I would then need to integrate this thing over space. So okay, I get here, instead of operating on this one, I kind of partially, I kind of use the fact that I'm integrating a derivative. So this is kind of a substitution from 0 to infinity. Of course, this is completely crazy. I think there's a better way to, I think that the good way to do this is that you should probably regularize this integral somehow, and I didn't bother, okay? So anyway, these, and this is, so what you get, I think, is, I'm not sure about the 2 pi, because I'm not very sure about this, right? But what happens is that, what happens anyway is that somehow, one way or the other, you can convince yourself that the nabla squared acting on a log in 2 dimensions is a delta function. And then basically this is telling you that, okay, because this is 1 over k squared, so it means that if I take a nabla squared of this, I differentiate this with respect to x, you know that when I'm differentiating with respect to x, it's the same as multiplying by k squared. Multiplying by k squared cancels this, and then this becomes a delta function. So the nabla squared of this is a delta function in x. So if I know that nabla squared of log is a delta function, then I can convince myself that this is, then I assume this is 1 over 2 pi. I'm not sure about the 2 pi's. Anyway, there's some coefficient, some pi's, and a log. So this is actually the physics. So just maybe something that is more familiar to you is in 3 dimensions. In elementary physics, you do Newton's gravity or Coulomb law, electromagnetism. You know that the 1 over r, so that this integral in 3 dimensions, a Fourier transform of 1 over k squared is 1 over r, 1 over 4 pi, 1 over r. So the Coulomb field, in 3 dimensions, the Coulomb field of a point-like charge goes like 1 over r. In 2 dimensions, the Coulomb field of a point-like charge is a log in r. It's very weird, okay? And then I just thought, okay, so here I just put some cutoff, because a log of a dimensionful quantity is not very meaningful. The point here is that somehow, in the end, physics, this is not a physical observable, right? A physical observable is something like an electric field or a magnetic field, and these are all derivatives of the gauge potential. So I can have a gauge potential that depends on some cutoff that I don't know, but the electric and magnetic fields that this gauge potential corresponds to are going to be derivatives of this, and the scale under the log drops out. So when I differentiate this expression to calculate the electric field of a point-like charge, this doesn't matter, and the electric field of a point-like charge goes like 1 over r in 2 dimensions. Whereas in 3 dimensions, you remember from elementary physics that the electric field of a point-like charge goes like 1 over r squared, or the gravitational acceleration of a point-like mass goes like 1 over r squared. In 2 dimensions, the potential is a log, and the potential is a log, and then the field, electric field or magnetic field, is 1 over r. Okay, so this is the kind of a field. This is the kind of a field that you would have for a point-like charge. So notice here, kind of, this is the delta function in independent of one coordinate, delta function in another coordinate. This is just like the structure of this CGC field of one nucleus that we have been discussing. Good. So as I said, I'm unsure about the 2 pi's. I think you can probably go Google and find a better reference for how to invert this 2-dimensional propagator and get the pi's right. I think this is taken from Yuri's and Zhenya's book, and I think Yuri is a careful. I wouldn't trust Zhenya with 2 pi's, but I do trust Yuri. So I think this expression is probably correct because it's from Yuri's book. I trust Yuri with 2 pies. On the other hand, I don't necessarily understand Yuri's 2 pies because he puts 2s and pies in different places than I would put them. But I think he's correct. But I'm not always sure about the intermediate steps. Okay, good. Do you want to think about problem number 2 for a few minutes, or well, let's think about it for a few minutes so that I write something down on the board in the meanwhile. I remember, but then and somehow, depending on the situation, I use two different conventions, and I can never remember which one I'm using. Yes. Okay, so first, correct the problem, right? I think this is probably a calculation many of you have done. Somehow, maybe when you were first introduced to non-abelian gauge theory. So I believe, yes, and one would think that the signs would cancel, but they don't, because it's a nonlinear thing. So somehow the sign here is correlated with the sign here, and I got it wrong. So let me change this to minus, okay, in the problem, and then I can keep this. So let's start with A. So if I here have a minus, right? So I'm just plugging. So this field is known as this kind of a field is known as a pure gauge. So it is a field that you can obtain by taking the vacuum and making a gauge transformation to the vacuum, right? So this is obtained by taking a zero field and gauge transforming, and things that are gauge invariant and physical measurable, like the field strength tensor, because somehow that tells you about the energy of the system. F mu nu squared is the Lagrangian, and squares of components of F mu nu are energy densities. So they have to be zero if this is gauge equivalent to a vacuum, right? So let's check how it is. So we just take this, and here we plug it in. So we take a derivative of u of this derivative of a mu minus mu derivative of a nu, and then the commutator term. Okay, so here I have a derivative of a product. So there's two terms. I differentiate either this, like this, or I differentiate the second thing. So I get a second derivative of this u dagger. Same thing for this one, I get two terms. These are immediately cancel each other, d mu, d nu. These are just ordinary derivatives. They are the same, and there's a relative minus sign. And so this is kind of like the abelian-like term. And then I have these two leftover terms. Then I have the commutator. We're now correcting the sign in the problem. Minus ig, and then this I squared over g squared is this I over g. Okay, so altogether I need a plus I here, okay? And so this becomes a plus, right? And then I write out the commutator. So the commutator is two terms, this times this minus this times this. Okay, so here I have, in this times this, I have things like, that are u, derivative of u dagger u, derivative of u dagger, and somehow that needs to cancel against this. So this is true if I recognize that u derivative of u dagger u is actually minus the derivative of u, right? How do I know this? The justification is here. I know that U is a unitary matrix. So U dagger U is just the identity matrix. So derivative of U dagger U or U dagger is 0. On the other hand, if I use the rule for differentiating a product, derivative of this product is the derivative of the first term plus the derivative of the second term. And then I can multiply this equation. What do I need? I multiply this, so I have a 0 equals this. I multiply this equation from the left by u. No, I want to multiply it from the right by u. So I get 0 is d mu u, u dagger u plus u d mu u dagger u. I just multiply this equation from the right by u, and this is again 1. So a derivative of u is u, derivative u dagger u, and the minus sign from moving one of these terms to the other side of the equation. So thus I know that this is just a derivative of u, and then Now with the corrected signs, these terms cancel each other, and this term cancels against this term. Okay, so that's a pure gauge, and what we'll see not tomorrow but the day after. So kind of tomorrow we will discuss this kind of physics. The day after we will discuss this kind of physics. So now for an abelian theory, the sum of two pure gauges is not a pure gauge, but what we'll see, and this is the thing that gives you the magnetic field, in the longitudinal magnetic field in the plasma. So you take a field that is a sum of two such pure gauges. So both of these are individually vacuum equivalent. But now I calculate the sum, and now I start calculating. So what we're going to be interested in the plasma is the case where these are transverse components of the gauge field. So Fij, where I and j are transverse, this is the longitudinal magnetic field. So I and j are x and y components, and then this component of F mu nu corresponds to the z component of the color magnetic field. So the z component of the color magnetic field for a field that is a sum of two fields which are both separately gauge equivalent to the vacuum, I just plug it in. The things that only involve, so there's a thing that involves the derivatives of the first field and then the commutator of the first field with itself. These go away because I know that this kind of a field has a zero F mu nu. The only thing that survives is the terms that are kind of crosses. So AI of the first AI commutator with the J component of the other one, and then the I component of this one commutator with the J component of the other one. So this is going to be the Z component of the chromomagnetic field in the plasma. Good. And now I think we're 5 minutes over time. Time to take a break, and then Guillermo will continue.